Now, for our last method of heat transfer, we have radiation. Radiation is a transfer of the heat by electromagnetic waves such as visible light, infrared, and ultraviolet radiation. Everyone has felt the warmth of the sun's radiation and the intense heat from a charcoal grill or the glowing coals of a fireplace. Most of the heat from these very hot bodies reaches you not by conduction, in which requires contact between two bodies, nor by convection in the intervening air, which there must be a fluid flow, instead by radiation. So this heat transfer would occur even if there was nothing but vacuum between you and the source of heat. Just like our sun, that transfer its heat through radiation, although there is a vacuum between these two celestial bodies. Everybody, everything, every object, even at ordinary temperature, emits energy in the form of electromagnetic radiation. Around 20 degrees Celsius, nearly all the energy is carried by infrared waves with wavelengths much larger than those of visible lights. As the temperature rises, the wavelengths shift to shorter values. At 800 degrees Celsius, a body emits enough visible radiation to appear red hot, just like this iron rod that being exposed to heat. It radiates or its color change into red hot. Although even at this temperature, most of the energy is carried by infrared waves. At 300 degrees Celsius, the temperature of the incandescent lamp filament, the radiation contains enough visible light that the body appear white hot. In the transfer of energy by radiation, the absorption of electromagnetic waves is just as important as their emission. The surface of an object plays a significant role in determining how much radiant energy the object will absorb or emit. For example, these two blocks in sunlight, as illustrated, are identical, except that one has a rough surface coated with lamp black, and the other one is highly polished with silver surface. As a thermometer indicates, the temperature of the black block rises at a much faster rate than at the silver block. This is because lamp black absorbs 97% of the incident radiant energy, while the silvery surface absorbs only 10%. The remaining part of the incident energy is reflected in each case. We see that, that the lamp black is black in color because it reflects so little of the light falling on it, while the silvery surface looks like a mirror because it reflects so much light. Since the color black is observed with nearly complete absorption of visible light, the term perfect black body or black body in simple is used when referring to an object that absorbs all the electromagnetic waves falling on it. All objects emit and absorb electromagnetic waves simultaneously. When a body has the same constant temperature as its surroundings, the amount of radiant energy being absorbed must balance the amount being emitted in a given interval of time. The block coated with lamp black absorbs and emits the same amount of radiant energy, and the silvery black does too. In either case, if absorption were greater than emission, the black would experience a net gain in energy. As a result, the temperature of the black would rise and not be constant. Similarly, if emission were greater than absorption, the temperature would fall. Since absorption and emission are balanced, a material that is good absorber, like the lamp black, is also a good emitter of heat. And material that is poor absorber, like polished silver, is also a poor emitter of heat. So a perfect black body being a perfect absorber is also a perfect emitter. Just like our summer clothing, the fact that a black surface is both good absorber and a good emitter is the reason people are uncomfortable wearing dark clothes during summer. Dark clothes absorb a large fraction of the sun's radiation and then re-emit it in all directions. Light color clothes, in contrast, are cooler to wear because they absorb and re-emit relatively little of the incident radiation. Now let's have this formula. So the rate of energy radiation from a surface is proportional to the surface area and the part power of the absolute temperature, which measured in Kelvin, and the rate also depends on the nature of the surface. So this dependence is described as a quantity E, or called emissivity. So a dimensionless number between 0 and 1. So again, this is a dimensionless quantity. So E represents the ratio of the rate of radiation from a particular surface to the rate of radiation from an equal area of an ideal radiating surface of the same temperature. So for a perfect black body, the emissivity is 1. Thus, the heat current H, which also Q over T, which is the rate due to the radiation from surface area A with emissivity E at absolute temperature T, can be expressed in this formula. Whereas we have this quantity, which is a fundamental physical constant called Stefan Boltzmann constant, which is equal to 5.67 times 10 raised to negative 8 watts per square meter times to the fourth of Kelvin. So let's have an example problem. A supergiant star Betelgeuse has a surface temperature of about 2,900 Kelvin and emits a radiant power of approximately 4 times 10 raised to 30 watts, about 10,000 times as great as the sun. Assuming that the Betelgeuse is a perfect emitter, which is equal to 1, and spherical, find its radius. So we're looking for the radius. So the area, the surface area for a spherical object is equal to 4 pi r squared. So we're looking here for r. So we know that H is equal to A times the emissivity times the constant times T raised to 4. And H is equal to Q over T. So A, area, is equal to Q over T all over E raised to the 1. Okay. And substituting the formula for area, wherein area is equal to 4 pi r squared is equal to Q over T over this one. Therefore, radius is equal to the square root of Q over T all over 4 pi. So substituting the values, so we have 4 times 10 raised to 30 joule per seconds, or simply watts, all over 4 pi times the emissivity of 1 times our constant of 5.67 times 10 raised to 8 joules per seconds. And we know that joule per seconds is watts. So over the square of meter times raised to 4 of Kelvin times temperature of 2,900 Kelvin raised to 4th power. Therefore, our radius, calculating this one, is equal to 3 times 10 raised to 11 meter. So this is the radius of this supergiant star. So that is the Stefan Boltzmann law. Okay, so let's have our test your understanding by solving this problem.